Hello, this is Stuart Mason from Math 156/E156. We're talking about script 8b, which is estimation using the method of moments. This is kind of a funny ordering, really. The method of moments is algebraically messier than the maximum likelihood estimator, and it's also sort of outdated because with computers and the ability to optimize multidimensional functions, MLE is now much more widely used, but the method of moments is still useful theoretical tool to know, and also illustrates some other concepts kind of nicely, and so we're going to tackle it in this script. Cool, so let's start by generating 20 draws from a uniform distribution on 0, 8. So the idea for the method of moments is that we know the moments of different distributions as a function of the parameters, and we can calculate sample moments. So we then invert those relationships and estimate the parameters based on what parameters would have yielded these moments. And so, as Paul says here, the number of sample moments must equal the number of parameters. So as many parameters as you need to estimate, that's how high up your order of sample moments has to go. This is basically the linear algebra idea that you need as many equations as you have unknowns. Okay, so the uniform distribution on 0 to beta, the theoretical mean, the population mean, is beta over 2. So we have a first sample moment, and that's the mean, that's our sample mean. And so we say, okay, well, if the mean should be beta over 2, then beta should be twice the mean. And we compute our sample mean, and that gives us an estimate for beta. And in this case, our estimate was 10. Now, it might work out such that your mean comes out less than half your greatest sample, in which case your data will be quote-unquote impossible. In other words, if your beta hat comes out to be 7, but you have observed a draw of 7.5, well then you know the max can't be 7, and so you know that there's something wrong with your estimate. So if we run this code a couple times, eventually we'll get at least one estimate greater than our beta hat. Yep, there it is. So what is max x? 7.177, and yet our beta hat was 6.9, and so we have a problem. And so this is basically an inefficient estimator of the mean. So we're going to do the same idea with an exponential distribution. So we'll take 20 draws from an exponential with lambda 2. Remember, the theoretical mean is a half, 1 over lambda. Cool. So the mean of our data happened to be 0.382. So 1 over that is going to be our estimate for lambda, which we'll call lambda hat. In this case, 2.6. So now Paul's going to say, we'll do this process 1,000 times, and let's see what happens. So our average value of the sample mean was well concentrated around the theoretical value of the expectation for an exponential distribution. And the median is there too. Paul points out that the median is going to be less than the mean. This is another way of saying that the distribution has a right skew. But in general, expectation of 1 over x is not the same thing as 1 over the expectation of x. This came up during our midterm presentations, and of course it's the same here. So theoretical value is not 2, and this comes out to be somewhat bigger than 2. If we look at the histogram, you can see why. So basically the skewness of the exponential distribution persists here, and we have an asymmetrical distribution of data with too many values too far above the mean. And so more than half the time, our lambda is an overestimate. So Paul says, well, we only need 1 moment per parameter, but why use the first moment? Why not use the second moment? So let's take a look. The theoretical second moment is 2 over lambda squared. In this case, that's also a half. So we'll draw another random sample, and now this is our new estimator. And again, we're going to simulate this 1,000 times and see how it does. And again, our sample second moment comes out pretty close to the theoretical value. But our estimate for lambda got worse. Why is this? Well, by squaring the high values, we have exacerbated our skewness. The data is even more highly skewed, and so basically using the second moment has a higher spread, a higher probability of being wrong. And that's why we're better off using the first moment, although we can still do even better. So now we're going to use two sample moments to estimate two parameters. In this case, we're going to basically shift the exponential distribution forward, so it's a distribution with a lower limit. So it can start at 4, and other than that, it's a regular distribution with lambda equals 2. So here's what it looks like. It's basically an exponential distribution that you're used to seeing, but shifted to begin at 4. First two sample moments come easily enough, 4.42 and 19.7. And I guess there's some messy algebra that we can basically skip. The variance of an exponential distribution is known to be 1 over lambda squared. And so Paul gets clever by computing a sample variance that's independent of delta. And then we get an estimate for lambda based only on the sample variance. Our estimate of delta bar is then a function of both moments, right? Because this variance calculation includes data about M2 and M1. And we have a similar problem to the uniform case where if we get a delta bar greater than 4, but some of our data are less than that delta bar, but greater than 4, then we'll have generated like an impossible estimator once again. So yeah, basically it happened twice there. So again, this method of moments, historically useful from before we had computers to like helpfully calculate the MLE of very large data sets. These days, really mainly useful for talking about comparing different estimators, which is what we've done in this script. So hope this was a helpful guide to what's going on here, and I'll see you guys on Wednesday.